We're now going to learn about discrete distributions that follow specific rules. When we made distributions for things like rolling two die and adding the sum of the faces together, or flipping three coins and looking for the number of heads, we could calculate the probabilities simply based on our knowledge of how to compute theoretical probabilities. For the next four distributions we're going to learn about, they involve some more complex situations where the experiments used for probability will follow very specific rules. The first of the distributions is called the hypergeometric distribution. For each distribution, we'll talk about what it is, what conditions and variables need to be provided for you to use the distribution, how to calculate the distribution in Excel, and specific formulas for the expected value and variance for the distribution. We'll do this for all of the four distributions we learn about. So the first is the hypergeometric distribution. It models the probability of success when you're making draws without replacement from a finite population. So an example of that might be if you're playing poker, you could have five cards in your hand in classic poker. If you want to find the probability that you have two aces in the five cards that you're dealt, that could be an example of something you could use to calculate the probability using the hypergeometric distribution. You can use the hypergeometric to find the probability that you get two aces exactly and three other cards. The reason that we can use the hypergeometric is you have the whole population size. That would be the 52 cards in the deck. We call that N, the population size. That's what meant by a finite population. You have to know the size of the population. For K, that's the number of successes in the population. So if we're talking about aces, there's four of them in the whole deck. And the number of draws, if you're getting a poker hand, that would be five cards in classic poker. And for X, the number of observed successes, that's what card you're looking for. So if we're specifically looking to count aces and we say we want the probability you have two of them in your hand, X, the number of observed successes would be two. The conditions that have to be met for the hypergeometric are that you need to have a fixed population size. So you need to know, like in a deck of cards, that there's exactly 52 cards. You also need to have only two possible outcomes. That's called binary. What's meant by that is you're looking for something specific, like you care about aces versus non-aces. You'll put them in only into those two broad categories. This doesn't apply if you're interested in something like counting aces, jacks, and queens. It would just be ace versus not an ace. Also, you have to sample without replacement. In Excel, the formula is quite simple to apply. It's called hypgeom.dist as a short form for hypergeometric distribution. And you put in all of the elements that we just described. The number that you get from the number of draws, the total number of successes in the population out of the population size. For the last argument, you'll always put false in this course. For the expected value, instead of having to do the long table method that we did here, there's a shortcut for any named distribution. For the hypergeometric, you can calculate the mean or the expected value just by taking the number of successes times the number of successes in the population divided by the population size. The variance is a much more complicated formula that involves the little n, and capital K. But there are formulas, so you don't have to use the whole table method. The best way to understand the hypergeometric distribution is to look at some examples. So for every single name distribution we talk about, we'll talk about what it is, then we'll actually compute the answers. So a candy dish contains 30 jelly beans and 20 gumdrops. 10 candies are picked at random. What is the probability that 5 of the 10 are gumdrops? So in this case, the binary outcome is it a gumdrop or is it a jelly bean? There's only two options. The fixed population size is we have 30 jelly beans and 20 gumdrops. That's 50 candies altogether. And we're sampling without replacement. That means we're not putting them back in. If we pick them out, we're going to eat them from the jar, so we can't put them back in. To calculate the chance from this question that 5 out of 10 are gumdrops, we use hyper.geom. Oh, I wrote that wrong, sorry. Hypgeom.dist. There we go. Once I have that written out, Excel shows you what you have to enter. The first is, it says sample underscore S. That means the number of successes in the sample. So 5 out of 10 need to be gumdrops. Then we have population success. So how many gumdrops are in the whole population? The question says there's 20 gumdrops in 50 candies. Then you always conclude with a false. So this formula gives you that there's a about 21.5% chance that from this candy jar, if you pick 10 candies, 5 out of 10 will be gumdrops. For a similar question, let's say we have a total of 200 balls in a bag that include 25 red. 40 balls are randomly selected out of the bag. Find the probability exactly 8 of them are red. Again, this is hypergeometric because we care about red or not red. We have a finite population of 200 balls and we are not putting them back in. So I use my hypgeomdist function again. We say we want 8 out of the 40 selected to be red. There are 25 red balls in the bag and 200 in all, and we always end with false. This is about a 6% probability that 8 out of the 40 balls selected would be red. And that's how you use the function in Excel to calculate the probabilities for you. So instead of having to figure out the probabilities like we did for the previous examples when we were looking at all the possible combinations like we did for the dice and calculating them ourselves, the function hypergeom.dist can calculate the probability for a hypergeometric distribution without you having to look at all the possibilities for how 8 out of the 40 balls can be red, because that would take a very long time to write out the combinations. We have another name distribution that is also very, very common. The binomial distribution is important in statistics because it occurs very frequently. The binomial distribution is different than the hypergeometric because it's the number of successes with replacement. So, with the hypergeometric distribution, it was the number of successes when we had without replacement. With the binomial distribution, the picks are made with replacement. Also, something else different about the binomial distribution is you don't need to know the sample size or population size, rather, I mean. You're not going to be given the population size. For the binomial distribution, you just need to know how many choices you make. That's called the number of trials. Then you need to know the probability of success and the number of potential successes you're looking for in the question. So something is binomial if there are two possible options, success versus failure, and if there's a fixed number of trials. So that means you know how many picks you're going to make. For each pick, you maintain a constant probability. That's kind of like for rolling a die. You always have a constant probability of 1 in 6 chance for each side, and they're independent because they're with replacement. Remember, with replacement means you have independence. Just like in Excel, you had hypergeom or hypgeom.dist for the hypergeometric. In Excel for the binomial, there's a function called binomdist that takes the 3 variables that you need for the binomial distribution. The number of successes you're looking for, the total number of picks, and the probability of a success. Again, there are shortened formulas for the expected value and the variance of the binomial distribution. The expected value will simply be n times p, and the variance will be n times p times 1 minus p. So to see how these questions differ from the hypergeometric, let's look at some examples. A trainer is teaching a rescued dolphin to catch live fish before returning it to the wild. The probability that the dolphin successfully catches a fish is 35%, and the probability that the dolphin does not successfully perform the trick is 65%. Out of 20 attempts, you want to find the probability the dolphin succeeds 12 times. So in this case, the probability the dolphin is catching the fish is assumed to be 35% and it doesn't change. That's its past success rate we'll use for P. We have a recorded number of attempts, 20. That's the number of trials, N. And we want to find the probability to succeed 12 times. That would be X, our number of successes we are concerned with. To calculate that probability, you don't have to look at every single way a dolphin can succeed 12 out of 20 times. So you don't have to go like success, 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 failure, failure, and do all the combinations. You can just do binomial.dist with those elements that they succeed 12 times in 20. They have a probability of success of 35%. You enter it as a decimal, and then for the last argument, we always put false, just like for the hypergeometric, we set that to false. And the probability is only about 1.4% that the dolphin would succeed exactly 12 times out of 20. Another example, in a region of a country, 5% of all cell phone calls are dropped. What is the probability that 2 out of 6 randomly selected calls are dropped? So again, if I'm using binomial.dist for this one, we have 2 out of 6 calls dropped with the probability of dropping of 5%. You have to write it as a decimal and not as a percent. This is binomial because we have that there's 6 calls. That's the number of trials. 2 is our X, the number out of 6 we're concerned with. And we have a constant probability that's given to us. For the last argument, put false, and that gives us about a 3% chance that 2 out of the 6 would be dropped. So a less common distribution we're moving on to next is called the geometric distribution. Geometric is different because it can continue for a longer time because it's modeling the number of trials until you succeed. So for the binomial, you have to have a fixed number of trials. What that means is you definitely have 6 calls, or the dolphin will attempt the trick 20 times. For a geometric, instead of specifying the exact number of calls or tricks, you would say that you keep going until something happens. So with the phone calls, you keep making calls until one is dropped. With the dolphin, you'd keep getting it to attempt the trick until they succeed. So that's what's different with the geometric. You don't have a specific number of trials. You keep going until you get a success. A success is what you want to happen. For the geometric distribution, you'll need the probability of getting a success and when you're expecting that first success to occur, the number of trials. It has very similar conditions to the binomial, that you have to have independent trials with constant probability. How we calculate it in Excel is it's actually called the negative binomial or neg binom.dist. You'll enter the number of successes minus 1 for how many failures you have. 1 will be when you're getting that success, and P will be your probability of success. There are shortcut formulas again for the expected value and the variance written here. The expected value is 1 over P, the variance 1 minus P divided by P squared. I'll show you some examples of how we can use the neg binom.dist formula to solve for the geometric distribution. So you play a game of chance that you can either win or lose until you lose. Your probability of losing is 57%. What is the probability that it takes 5 games until you lose? So for this one, we're playing until we lose. So that's your hint that it's geometric. So for neg binom.dist, first you enter when the failure happens, or how many failures you have actually is how I should word that. So basically, if you're winning, if the question's asking, what is the probability it takes 5 games until you lose, then you'd play 4 and you'd lose on the 5th. You always enter 1 as the second argument. And the number that's given in the question, like 5 games until you lose, then minus 1 for how many non-successes you have. For the probability that has to be given in the question is 57%, and we always put false for the final argument. So again, if it takes 5 games until you lose, then you have to play 4. Then on the 4 plus 1, the fifth, you lose, and you have 57% chance of a loss. This will give you the probability that it takes you 5 games to lose. It's only 1.9% that it takes 5 games to lose. Another question, assume that the probability of a defective computer component is 2%. Components are randomly selected. Find the probability that the first defect is caused by the 7th component tested. So again, this is asking you for failure at the 7th test. So you'd have 6 times before you fail. 6 plus 1 is 7. The probability of failure is 2%, and we always put false for the last argument. This is about a 1.77% chance that the first defect would be on the 7th component only. So the hypergeometric, the binomial, and the geometric all involve some kind of sampling with or without replacement. The discrete distribution that is most different is the Poisson distribution. It's quite different than the rest. The reason that it's different than the rest is because it involves a time interval. It's the only distribution that involves a fixed interval of time, or it could be of space as well. If you have any question that's asking about an average rate or how much time it takes for an event, that's how you'll know it's a Poisson, because those are the variables involved for this distribution. The Poisson will involve independent events. You have to have a constant rate of time, and often the question will involve something rare to happen. In Excel, just like we had the hypergeometric and binomial formulas, we have a specific one for the Poisson distribution called Poisson.dist. There's also shortcuts for the expected value and the variance. For the Poisson distribution, both the expected value and the variance will be lambda. Lambda is the rate of time from the question. So again, these questions, the hint that you have a Poisson distribution will be that you have time involved in the question. So let's answer some of those probability calculation questions. Our first one. An insurance company determines the likelihood a man aged 25 will die within the next year is 0.0002, so very low. If the company sells 4,000 policies to 25-year-old men this year, what is the probability it will pay on exactly one? So this involves time, that it says within the next year will these people die. What is the probability they'll pay exactly one policy? So 1 is the X. The mean is that they have a chance of 0.0002 of dying, but we don't just have one person, we have 4,000. So to find what they call the mean or the lambda parameter, the average rate, you have to take that probability of them dying in the question and multiply it by the 4,000 people or policies that they're issuing to men. And you always end with false, just like for the other questions as well. This will give you the probability that they'll have to pay exactly one policy. It's about 36%, so it's fairly high, which makes sense if you have 4,000 25-year-old men, that it is possible that one of them could die and they'll have to pay the life insurance. The chance is about 36%. We have another related question. Leah receives about 6 telephone calls between 8 a.m. and 10 a.m. What is the probability that Leah receives more than one call in the next 15 minutes? This one's a bit tricky just because if you look at the question, you have this interval of 6 calls between 8 a.m. to 10 a.m. is given in hours, but this interval is given in minutes, the next 15 minutes. So we need to get those on a similar scale. What I mean by that is if we have 6 telephone calls in 2 hours, from 8 a.m. to 10 a.m. is 2 hours of time, then we would expect to receive about 3 per hour. How many 15-minute blocks are there in 1 hour? We have 4. 15, 30, 45, 1 hour. So if we have 3 phone calls per hour and 4 15-minute blocks in 1 hour, you should expect to receive about 0.75 calls in 15 minutes. This is what you call the rate parameter. The lambda, it's from the question because it's asking for the probability that she'll get more than one call in 15 minutes. We have to take the rate of telephone calls and put it into the 15-minute units because that's the probability the question's focused on. So let's say you wanted the probability that she gets 1 phone call. We could take 1 phone call, the lambda value that you expect to get about 0.75 phone calls in 15 minutes, and we always set the last option to false. So the probability of 1 phone call is about 35%. The problem that makes this question more complicated is it's not asking you for 1 phone call, it's more than 1 phone call. So you actually have to use the rule of complement here. Remember, the rule of complement is about opposites. So if we want more than 1 phone call, it could be 2, it could be 3, it could be 4, it could be 5, it could be 6, it could be 7, it could be 8. We don't know how many phone calls she could get in the next 15 minutes. It's technically like an unlimited amount. So what's easier than trying to find all those options is to do the opposite. The opposite of more than one is either getting 1 phone call or 0 phone calls. Those are the only things opposite of more than one. So how I use the rule of complement is I'd have to take the difference from 1 with getting 1 phone call and also including getting 0 phone calls, because that's technically also a possibility. That's opposite of more than one, because more than one is another way of saying 2 plus. The opposite of 2 plus is either 0 phone calls or 1 phone call. If I take both of those away from 100% or 1, that gives me the probability that she'll get more than 1 phone call in the next 15 minutes. It's only about a 17% chance that she'll get more than 1 in the next 15 minutes. So I know we went through a lot of distributions, but I have some learning check questions to help you recap which one to use when. Some quick tips I have before you try them out is for the hypergeometric, look for a population size and you won't be given any kind of probability percent. You'll just be given numbers. For the binomial distribution, you'll be given a probability and you have to have independent trials, so a fixed number of trials. For the geometric, the question will have to say something like you keep going or you keep trying until you have something specific happen. We call that our first success. And the Poisson is different because it's the only one that involves units of time or space where you have that average. Keeping those hints in mind, I want you to try answering these 4 questions. There's 1 question for each distribution, and then you'll have to use Excel to get the probability answer. Please pause the video here, and I'll show you the solution when you come back. Okay. So the first question is a call center receives an average of 3 calls per minute. What is the probability that exactly 5 calls will come in a minute? This one involves time, calls in a minute. So it is Poisson, the one that involves our time variable. For Poisson, we use the Poisson.dist function. This is asking for exactly 5 calls, so the first number is 5. For the second number, for the mean, in our practices, we had to do some calculations, like multiply the 0.0002 times 4,000, and we had to find out how many calls in 15 minutes instead of the calls in 2 hours. But in this one, the average is per minute, and we're asking about 5 calls per minute. So because everything's in minutes, you don't have to do any calculation for the mean. Just, it's 3. because all the units of time in this question are already the same. They're all minutes. And we always put false for the last argument. That's going to be about 10%. The next question. A basketball player has a 70% chance of making a free throw. If she takes 10 shots, what is the probability of getting 7? So this question involves a probability of success, and it has a fixed number of shots, that they take 10 no matter what. When you have a fixed number of shots, that's binomial. So this one will be binom.dist, that she makes 7 out of 10 shots. Her probability of making a shot is 70%. You have to write it as a decimal. So 7 out of 10, 70% chance. The probability she makes exactly 7 out of 10 is about 27%. The next one. A student guesses randomly on a multiple choice question with 4 options. What is the probability that the first correct answer is on the third question? So this one tells you that you're going to keep going until you get your first correct answer on the third question. Anytime you're stopping when the first success occurs means it's geometric. For geometric, we use the function in Excel called neg_binom, that if their first correct answer is on the third question, that means that the first 2 questions were wrong. They got the right answer on the third question. 2 plus 1 is 3. On a multiple choice test, what's the probability of getting the right answer if you're guessing randomly when there's only 4 choices? 1 in 4, or 0.25. You could type it as a decimal, and false is always our last argument. So the probability isn't really given to you in this question, but you have to figure it out. Knowing that there's 4 options for every question, you have a 1 in 4 chance of getting it right. So the probability that the first correct answer would be on the third question is about 14%. And finally, a deck contains 10 red cards and 40 black cards. If 8 cards are drawn without replacement, what is the probability 3 of them are red? So our only distribution without replacement and that you have the population size is hypergeometric. For hypergeometric, it's hypergeom.dist, where we're getting 3 cards and we're picking 8 cards. In the deck, there's 10 red and there's 50 cards altogether, the 10 red plus the 40 black. Always put false as your last argument, and you should have got 0.147 for your probability of getting 3 out of 8 cards red. And that is it for this lesson. I hope that you're able to get those 4 numbers, or you understand how to get them now that we've talked through the solution. But if you have any questions about discrete probability distributions after this lesson, please feel free to reach out to me and I'll be happy to help you. This lesson leads nicely into our next lesson, where we'll pick up where we left off in the first part. We talked about discrete random variables in this lesson. The next one, we'll move on to talking about the continuous random variable distributions instead of just focusing on discrete. Thanks for watching this video. See you next time.